Okay, thank you very much for the opportunity to speak. I'm going to be discussing a recent paper with Juan Maldacena, which in turn was inspired and informed by a series of talks given by Kitaev at KITP. To a large extent, what we were doing in this paper was verifying and elaborating on some of the results and conjectures that Kitaev had made. I should also mention that some work has been done on this model by Joe Polchinski and Vladimir Rosenhaus, and I think Vladimir will be talking a little bit about that during one of the sessions on Thursday. So the Sachdev-Kitaev model is a quantum mechanics system that shares some properties with black holes and seems to be our first data point on AdS2 CFT1 duality. One of the interesting things about it is that it's a strongly interacting system, but it's exactly solvable in the 1 over n expansion. And by way of motivation, let me just comment that it would be very nice to have a solvable model holography. To put this in context a little bit, the benchmark holographic theory, the large N strongly coupled super-Yang-Mills theory, is dual to Einstein gravity plus high tension strings corresponding to operators with very large anomalous dimensions. This thing is, it's a theory that describes black holes, and by a certain precise criterion, it's maximally chaotic. But it does not seem to be solvable in the 1 over n expansion, particularly at finite temperature, although some exact results are known. A typical representative of another class of holographic theories is the critical ON model in 3 dimensions. This guy is dual to Vasiliev gravity, which contains a whole tower of essentially massless higher spin fields, corresponding to operators with very small anomalous dimensions. This doesn't seem to describe black holes. It's only very weakly chaotic, but it is solvable in the 1 over n expansion. The model we'll discuss today is in some ways in between these two. It's solvable in the 1 over n expansion, but it's also, by the same criterion, maximally chaotic. The bulk dual contains, as we'll see, a sector which corresponds to dilaton gravity in 2-dimensional AdS, but it also contains a series of states that correspond roughly to what you might expect for a theory of strings with string length of order the AdS scale. These correspond to operators with order 1 anomalous dimensions. So, okay, it's not going to be a theory with as clean a holographic dual as the super-Yang-Mills theory, but we'll be able to use it to learn some things about AdS2 CFT1, and hopefully in the near future some things about black holes. Okay, before I start discussing the model in detail, it's helpful to have in mind a couple of properties the quantum mechanics system should have in order to be dual to AdS2. So first, at finite temperature, the system should describe a black hole in 2-dimensional AdS space. And in 2 dimensions, the area of the horizon is independent of temperature. So there should be a large entropy, even at very low temperature. This is an unusual property for a quantum mechanics system to have. We have all kinds of expectations for the 4-point function. For example, it should include a piece corresponding to gravitational scattering. And in the OPE, we can look at factorization and understand whatever spectrum of bulk fields we have in the dual theory. And then finally, you might naively expect a theory dual to AdS2 to be conformally invariant. And just to have the formula in front of your eyes, I've written here the 2-point function that's SL2R covariant for operators on a Euclidean time circle. So time tau is running between 0 and beta, the inverse temperature, and this is the SL2R covariant form. This is subtle, though, because in 1 dimension, you would expect the conformal group is not just SL2R, but it consists of all reparameterizations of time. And a theory that has that symmetry would have to be topological, which is not what we're interested in. So somehow that can't be an exact symmetry. But it's even worse than that, because it's possible to show that finite entropy and SL2R is enough to ensure that the theory would have to be topological. So somehow all of conformal symmetry is going to have to be only approximate in this model. Understanding the extent to which this system does and does not have conformal symmetry, and to which AdS2 does and does not have conformal symmetry, is probably the single most important thing to understand about these systems and how they're related to each other. Okay, so let's start. The Sachdev-Kitaev model is a quantum mechanics of n-Majorana fermions. These are quantum operators that anti-commute with each other and that square to a multiple of the identity. The Hamiltonian is just a sum of all possible 4 fermion interactions with coefficients j with indices that we take to be drawn from a Gaussian distribution with mean 0 and with a variance that's given here. The variance depends on this parameter capital J, which sets the scale of the Hamiltonian. The dimensionless coupling in this model is the inverse temperature beta times J, and the interesting behavior will be at strong coupling. We can think about this either as low temperature or as large J. It's sometimes useful to think about a slight generalization of the model where we have the fermions interact in groups of Q instead of 4. The reason is that Q goes to infinity and Q goes to 2 are simpler than Q equals 4. It's pretty clear that when Q goes to 2, this is simple, because then we just have fermions with a random mass matrix. So it's a free theory. Okay, a technical comment is just that this system, well, you can check numerically that it self-averages like a champion, so we don't need to worry about replicas in the analysis of the model. So the Hamiltonian in this form was written down by Kitaev. It's a refinement, in some ways an improvement, of the earlier spin system model that was discussed by Sachdev and Ye, hence the name Sachdev-Ye-Kitaev. So how can we analyze the system? One nice way to do it is to think about Feynman diagrams. So at large n, these are the Feynman diagrams one has to sum to compute the 2-point function. These are sometimes referred to as iterated watermelon diagrams. And these are the diagrams one has to sum to compute the 4-point function at leading order at large n. Each of the propagators here are supposed to be a sum of all the diagrams on the previous line. So there are well-established and nice techniques for summing this type of this class of diagrams. And this is a very physical way of thinking about the model, but it's not the one we're going to use in this talk. Instead, we're going to do the following. Of course, this is equivalent to thinking about the Feynman diagrams, but this is what we'll do instead. We think about integrating over this disorder, J, before we do the path integral. This gives us some rather unpleasant action involving bilocal action of the fermions. And it can be simplified a little bit by introducing 2 new fields, G and sigma. Each of these guys depends on a pair of times. The purpose of sigma is to be a Lagrange multiplier that sets this equation, sets G equal to an average bilinear of the fermions. I've colored this one red because I'm going to refer to it later. So the statement is that G will be this average bilinear of the fermions, and sigma enforces that. Yeah, the point of going through G and sigma is that then the fermions enter only quadratically, and so I apologize for just dropping this on you, but this is what one finds. You get the theory written in terms of these variables, just G and sigma. The fermions are gone, the disorder is gone, and we have this action. So it's a rather funny action, depending on these bilocal fields. This log determinant term comes from integrating out the fermions. The sigma G term is a leftover from the Lagrange multiplier. And then finally, this G to the Q term is the avatar in these variables of the psi to the Q interaction that we had in the Hamiltonian. Okay, a couple things to notice about this. Well, first, although I haven't gone through all the steps, I promise that this is an exact rewriting of the theory. In particular, this is true at finite n. It's true that this is exactly the disorder average theory. We haven't made any approximations. And second, the benefit of going through this, I mean, this action in some ways is rather unpleasant, but the benefit is this factor of n here. So n multiplies the entire action, so at large n, this is a semi-classical theory. In other words, G and sigma are what are sometimes called the large n master fields. They're the variables that become classical at large n. And in some way, we're supposed to build a bulk theory. We're supposed to build a holographic dual out of these variables. Okay. So the plan for the rest of the talk is very simple. We have a semi-classical integral with a large parameter here, and we're going to do the first 2 things you should always do in this sitting. First, we'll study the saddle point. This will allow us to learn about the two-point function and the entropy in the model. And then we'll study small fluctuations about the saddle. This will tell us about the four-point function and about conformal symmetry properties. So first, we'll discuss the saddle point. So you just take this action here, and you vary it with respect to g and sigma, and you get these equations, where fields with an asterisk are supposed to represent the saddle point values. These are somewhat complicated equations, but they can be solved numerically, or they can be solved exactly at large Q, and I'll just plot for you the types of solutions you get. So what I'm plotting here is g star, the saddle point value of g, as a function of the difference of its two time arguments. So remember from that red equation, g is a bilinear of the fermions, so the saddle point value of g gives us the large N two-point function of the fermions. So that's what this is a plot of. This is the two-point function of the fermions as a function of the separation along the Euclidean time circle. So time runs between 0 and beta, the inverse temperature. I plotted this for three different values of this dimensionless coupling, beta j. At weak coupling, or high temperature, the two-point function is almost exactly independent of time. But as we crank up the coupling, it starts to decrease and reaches a minimum halfway around the circle. You can actually analyze these models exactly at very large beta j, analyze these equations exactly at very large beta j. And what one finds is this SL2R covariant form that I had written earlier is the solution to these equations. If you go through the details, substituting this in here, you find that delta is equal to, delta, which is the conformal dimension of the fermion, is equal to 1 over q. So the model seems to be trying to pass one of these tests that a system is supposed to pass in order to be dual to AdS2. It has this form for the two-point function. So what can we do with this solution? One nice thing is to plug it back into the action and compute the saddle point value of the action. This gives us the large N approximation to the thermodynamics. So I've plotted here the entropy divided by N. You compute the entropy just from the log of the partition function, its derivative. And I've plotted that using the exact numerical solutions for three different values of Q. So first let's discuss this green curve. This is Q equals 2. Now remember, when Q is 2, we just have a quadratic Hamiltonian in terms of the fermions. There's a random mass matrix, but if we diagonalize that, that's a theory that's gapped. It has a reasonably large gap. So the entropy should go to 0 at low temperature, and indeed it does. But for Q bigger than 2, the entropy does not go to 0 at low temperature in this approximation. So indeed, we have a large entropy. It's extensive. It's proportional to N, even at very low temperatures. So this is another one of the properties that such a model was supposed to have. Okay. I should mention also that this Q equals 4 curve here, which is here computed from the saddle point, is in really excellent agreement with some exact diagonalization numerics that have been done by a collaboration at Stanford, including Guy Garari. Okay, so this is it for the saddle point. Next, we'll study fluctuations. So to do this, we expand the action to quadratic order about the saddle. In principle, the action depends on two fields, g and sigma. But to save writing, I'm just going to write things, I'm going to suppress sigma and just keep track of g. So we expand it about the saddle point plus a quadratic term. Delta g is the fluctuation about the saddle point, g star. This quadratic form here is a simple function of the saddle point values, g star. It's useful to think about it as a matrix where the first two time arguments are like the I index, and the second two time arguments are the j index. What can we do with this? A nice thing to do is to compute the 1 over n term, so the leading connected term in the fermion 4-point function. Specifically, we consider this 4-point function where we have two fermions of type A and two fermions of type B, and we average over the choices of A and B. Using that red equation, this is a 2-point function of the G field. G is bilinear in the fermions, so a 4-point function of the fermions is a 2-point function of G. And in the saddle point approximation, we have this disconnected piece here where we just evaluate this on the saddle point solution, and then we'll have a term that comes from the integral over the fluctuation delta G. That's just the inverse of the propagator, the propagator, well, that's the propagator which comes from inverting this quadratic form Q. Notice that we have a 1 over n because there was an n multiplying the entire action. Okay, so for generic values of beta j, this quadratic form here is very difficult to invert. But for large beta j, where we had this simple solution involving sine of tau, it's conformally invariant. So this makes it possible to diagonalize Q exactly. And we find the following 4-point function. I'm going to give you here the connected answer divided by the disconnected answer, which is this thing. And that looks like the following. First, we have an infinite piece, which comes from some zero modes of Q. I'll come back to that in a moment. But we also find a whole tower, a discrete tower, of conformally invariant terms. Chi here is a conformal cross ratio of the 4 times on the circle. And this expression here, chi to the h, times this hypergeometric function, is a conformal block in 1 dimension. So what this term represents is a contribution to the OPE from the operators that appear in the product of 2 of these fermions. The dimensions are roughly evenly spaced. I'm plotting here the first 6 of them. Roughly speaking, these operators that are appearing in the OPE correspond to a bilinear of the fermions with some time derivatives inserted. They have order 1 anomalous dimensions, which can be computed exactly. And, well, they demand, in a holographic interpretation, they demand a tower of bulk fields, which, somewhat reminiscent of a string spectrum with string tension of order the AdS scale. Okay, but now we have to understand these zero modes that were giving us an infinity. So first of all, why do we have zero modes in this quadratic form Q? The explanation of that is simple. At large beta j, the action turns out to be invariant under general reparameterizations of time. So this is an attempt by this model to be invariant under this full conformal group in 1 dimension. So if we take the saddle point solution we had written in terms of sine of tau, and we apply reparameterization, we get another saddle point solution. So there's not just one saddle, there's a whole family of these saddle points in the G sigma functional integral. And the zero modes are just corresponding to directions along that family of saddle points. Or in other words, these zero modes are like Nambu-Goldstone bosons for the spontaneously broken reparameterization symmetry. We're spontaneously breaking it by picking this particular saddle point, and so then we have these zero modes for the broken generators. Now, in the exact model, we don't have precise reparameterization invariance. So in order to fix this infinity we got from the zero modes, we have to compute the action, this quadratic form Q, to 1 higher order in beta j. This can be done by perturbation theory. What one finds is a correction, an eigenvalue of this quadratic form that's suppressed by 1 power of beta j. It's also proportional to the Fourier mode of the reparameterization that we're considering. And if you plug this back in, what you find is a corrected finite 4-point function, which looks like this. We have this contribution we had discussed previously from the non-zero modes, and then we have this term which used to be infinity. It's now, well, it's big, it's proportional to beta j, but it's multiplying a particular explicit and quite simple function of the times. There are like a million things to say about this contribution, but I'll limit myself to 4. The first one is that it dominates, right? Because it's multiplied by beta j, and beta j is large in the limit that we're working in. So it gives a numerically much larger contribution to the 4-point function than even this infinite sum of these other guys does. Another point is that it's not conformally invariant. It's not just a function of the conformal cross ratio, it's a function of 3 out of these 4 times independently. So, I mean, there's something, I guess, a little bit sad about this, that the model was trying to be reparameterization invariant, and it sort of backfired. And in the end, the 4-point function is dominated by its failure, by its failure to be conformally invariant. Okay. Another point, since this is an explicit function of the times, you can check that this contribution saturates the chaos bound, justifying the claim which was made earlier that this system is a maximally chaotic quantum system. And then finally, and maybe most interestingly, this function agrees exactly with the contribution to the 4-point function that you get in a very simple model of dilettante gravity in AdS2. So to explain that, well, the simplest way to explain that is to think about the effective action for these zero modes. That follows from this correction to the quadratic form here and from the fact that reparameterizations are always small if you look at them locally. The answer that you get, this was originally conjectured by Kitaev, but we checked it, is that the effective action for these zero modes is an action which is given by the Schwarzian derivative of the reparameterization f with respect to the physical time tau. So this action here turns out to exactly agree with the effective action that you get for this simple Almhiri-Polchinski-Jakiv-Teitelbaum model of dilettante gravity. This is something that's going to be discussed in the Gong Show by Zhenbin Yang later today. The basic point is that the dilettante gravity theory reduces to just a single, the only degree of freedom is this reparameterization of time, f, and then it's possible to just check from the action that the action for that mode is the Schwarzian derivative. Okay. So this justifies the statement that this model describes dilettante gravity in addition to this tower of massive states. Okay, so the last comment I'll make is a comparison between this contribution f big that we got here from these reparameterizations and somewhat similar contribution that you get to the 4-point function in a two-dimensional conformal field theory, which comes from the exchange of the stress tensor, the factorization on the stress tensor. Both of these things can be associated to reparameterizations. In the two-dimensional case, they're holomorphic reparameterizations, and in our case, they were just one-dimensional reparameterizations. In a holographic setting, you interpret these things as boundary gravitons in both cases. There are other similarities between them, like, for example, this contribution to the 4-point function encodes energy fluctuations in the system, in the OPE region, and if it was the only term in town, it would saturate the chaos bound in both cases, including in the two-dimensional CFT case. But what's more interesting is the difference between this and what we have in 2 dimensions. So there are two important differences. One is that in 2 dimensions, the contribution from this stress tensor is conformal. And here it's not. The expression that we got was not conformally invariant. This is related to the fact that these reparameterizations have a conformally invariant action, which is related to the Weyl in 2 dimensions. And then finally, this, in 2 dimensions, for the stress tensor to dominate the 4-point function requires special conditions on the spectrum of the theory. For example, in the chaos limit, generically it will not dominate, and it will not saturate the chaos bound, even though the stress tensor by itself would have saturated the chaos bound. This is like the statement that to get a holographic theory requires, it's a non-generic thing. It requires a sparse spectrum in 2 dimensions. But here, this particular piece dominates the 4-point function automatically because of the beta J enhancement. We didn't have a terribly sparse spectrum. We had these low-lying, roughly evenly spaced massive modes, but still this reparameterization term dominates the 4-point function because of this extra enhancement that we got. Okay, so let me just summarize. This Sachdev-Kitaev model seems to be a very interesting, solvable quantum mechanics system. As we saw, the dominant low-energy physics is determined by spontaneously and then weakly, explicitly broken conformal symmetry. That's reparameterization symmetry in time. This aspect turns out to be precisely shared with dilettante gravity in AdS2. Zhenbin will comment more on that in the Gong Show. In addition to this sector, the model has a tower of states that are vaguely reminiscent of a stringy dual with tension of order the AdS scale. Okay, that's it. Thank you very much.
The effective action which you wrote has a form of the Hamiltonian of the action of L0 on the orbit of Virasoro algebra, S1 by S of R. which also has other orbits, like E+1 by U1. Do you know what you should, how do you modify the SYK model to produce other orbits?
I didn't understand that. Which, you're talking about the Schwarzian derivative action?
Yeah, Schwarzian derivative.
And what was the statement about that?
So the F, your variable, the entire variable is it's diffeomorphism of the circle.
Yes.
But you actually divide by SL2R because it's the invariance of the section.
Yeah. So that action is invariant under SL2R transformation.
Right.
So that's like a gauge symmetry in this model.
So this action, the variable is it's a point on the orbit. So this cosine space is orbit.
Yeah, that's right. That's right.
And so the Hamiltonian we showed is it's actually L0. It's one of the infinite series of commutative Hamiltonians of KdV character. So you can either, so there are two questions there. So there are other orbits. So there might be other models which we do to, and there are also other Hamiltonians which we write, which means that maybe you also have models which we write.
Okay. That's interesting. Yeah, let's talk about this. Thanks for that comment.
So you have introduced these large and master fields, and my question is, do these fields satisfy quantum Boltzmann statistic, and if it's so, can you make somehow direct connection from the quantum chaos in this model to classical chaos by considering some kind of kinetic equation?
Do they satisfy what? Sorry, could you?
Quantum Boltzmann statistic. Q-deformed statistic with Q equals to R. Particular.
I'm not sure what that is. You're asking whether the G sigma system is chaotic, or?
No. There were papers in late 90s about large and master fields in matrix models, and these fields satisfied quantum Boltzmann statistic. So I'm asking you if this is the case in your model.
Okay, I don't actually know what you're saying. Quantum something statistic, but
it's when commutator of creation and annihilation operators is just
there's a formalism for solving some of the large M theories in terms of free probability theory. So it's not
Okay. Thanks for that comment as well. You guys are a very advanced audience.
Can you calculate the quantum entropy in this theory and therefore try to find an alpha prime exact from the generalization of the hierarchy?
Well, yeah. I mean, you can compute the entropy. So there's a zero temperature component of the entropy at large n, and then there's also a piece which depends on the temperature, which comes from this Schwarzian derivative action. Yeah, one difference, in terms of this session that we've had today, is that in this model, entanglement entropy between subsystems is a completely useless concept. So it seems like an interesting testing ground also for thinking about ways in which the geometry can emerge that don't rely on spatial entanglement as a type of order parameter.
Do you think that at large n but finite beta j, this does actually have a string dual, or is that impossible? Just literally a classical string theory?
I don't know of one. It seems possible, but I don't know I don't have a worldsheet theory in mind. That's what you're asking. Yeah. It would be very interesting if it did, but I don't know.
Sorry, just to follow up, but did the operator spectrum have an exponential growth, or more like Vasily growth?
No, it's like one trajectory, but that's what you would expect in 2 dimensions. You don't have oscillators, so
I see.
yeah. There's a question up there.
I'd like to sort of make the comment which is very similar to what Nikita said, that in some work that we are almost doing, completing, that if you take the Virasoro group and look at the coadjoint orbit based on the subgroup SL2R, then the natural action that appears in that theory is the Liouville action. So it might be actually reasonable to propose that the bulk dual theory is a non-critical string theory, which is the Liouville theory with a cosmological constant. And if you do, with the appropriate boundary term, and if you do a calculation in this type of dual, we do obtain this Schwarzschild term that you obtain for the effective action of the Goldstone nodes in your one-dimensional field.
Oh, that's very interesting. What is? Could you say again? What is the bulk theory that you have?
The theory is the Liouville theory with the appropriate boundary terms.
Okay.
Just as a proposal, it definitely reproduces the Schwarzschild action which you have for the Goldstone nodes. Whether it really reproduces the full spectrum of the...
Yeah, that would be harder, but you say that just reduces exactly to just this boundary mode?
Yes.
Okay, that's interesting.